All right, let's take a deep dive into satellites and orbital mechanics. I know a lot of you out there are interested in how satellites stay up in space,
hmm
you know, circling the Earth without just falling right back down. We've got some cool stuff to look at today, like this JavaScript simulation from Open Educational Resources, open source physics at Singapore. Did you know that not all those orbits are perfect circles?
Yeah, it's pretty amazing how those orbits actually work when you get into the details.
Yeah, I always picture like a model, those little balls and the wires like perfectly spaced out.
Yeah, a lot of people start there. But think about this. If you were swinging a ball on a string, how would you keep it in a perfect circle?
You'd have to keep your hand really steady
Yeah,
and keep swinging at the same speed.
exactly. Now try to do that with a satellite hundreds of kilometers above Earth. You've got gravity acting like that string, pulling the satellite towards the center of the Earth.
So gravity is super important. But how do you find that sweet spot where gravity doesn't just pull it all the way down?
That's where orbital speed comes in. And why those perfect circles are more like the exception, not the rule. It's this balance between the force of gravity and the satellite's forward motion. Too slow, and it'll fall back to Earth. Too fast, and could escape Earth's gravity completely, but at just the right speed, it'll fall around the Earth, constantly being pulled towards the center, but never quite getting there.
Okay, so orbital speed, you mentioned a formula earlier.
Okay. It's v equals the square root of g times m over rv is the speed needed for orbit. G is the gravitational constant, m is the mass of the Earth, and r is the radius of the orbit.
So the farther out a satellite is, the bigger r is.
That's right. And since r is on the bottom of that fraction, as r gets larger, the orbital speed actually decreases. So a satellite orbiting farther away from Earth needs to travel slower to stay in orbit. It might seem a little weird, but it makes sense when you think about gravity getting weaker with distance.
That's really cool. Like the farther out you go, the less you have to worry about speed. But what about the opposite? What if a satellite suddenly slows down?
That's where things get really interesting, and where those simple circular orbits kind of break down. Most real orbits are elliptical, not perfectly circular. Remember that student in the article who thought a slower satellite would just move into a smaller circular orbit?
Oh, yeah. They thought it was that simple.
Well, the simulation shows what really happens. When you slow a satellite down, it doesn't just jump to a smaller circle. The orbit stretches out and becomes more oval-shaped, or as we call it in physics, elliptical. Like if you pulled on one side of a rubber band.
Whoa. Seeing it in the simulation makes it so clear. So why are elliptical orbits more common than perfect circles?
Because there's so much more going on than just Earth's gravity. You've got the moon, the sun, even other planets all pulling on the satellite a little bit. And Earth's own gravity isn't perfectly even everywhere. All these things can nudge the satellite off a perfect circle and create that elliptical shape.
Wow. It's like a giant cosmic dance. I'm starting to get why those perfect circles are so rare. But if the satellite's path is always changing in an elliptical orbit, doesn't that mean its speed is changing too?
Exactly. That's one of the key things about elliptical orbits.
Okay, this is getting complex, but in a good way. I think we need to take a minute here to let this all sink in. For everyone listening, and for me too.
I think that's a great idea. We've covered a lot of ground already. It's good to make sure everything's clear before we move on.
Okay, I think I'm starting to wrap my head around these elliptical orbits.
Yeah.
Like a whole new way of looking at how satellites move.
Yeah, it definitely changes your perspective. And understanding elliptical orbits is so important for understanding how satellites work and what kind of orbits are best for different missions.
Speaking of which, you mentioned that a satellite's speed is always changing in an elliptical orbit. Could you explain that a little more? It's like it would be speeding up and slowing down constantly, like a roller coaster.
That's a good analogy. A satellite in an elliptical orbit does travel at different speeds at different points. It moves fastest when it's closest to Earth, at a point we call perigee, and slowest when it's farthest away at apogee.
So it's like it gets flung around the Earth, speeding up as it gets closer, then slowing down as it moves away. But how does that work with that formula we talked about for orbital speed? That formula assumes a constant radius. But in an elliptical orbit, the distance is always changing.
You got it. That's a really important point. That formula v equals square root of gm over r. Works great for calculating the speed needed for a circular orbit at a specific radius. But for elliptical orbits, where that radius is always changing, We need to use something a little more advanced. It's called Kepler's laws of planetary motion.
Kepler's laws.
Yeah, they help us understand the geometry and dynamics of elliptical orbits, including how the speed changes at different points. It gets a bit more complex mathematically, but the basic idea is still the same. That interplay between gravity and a satellite's forward momentum is what determines its path and speed.
Okay, so even though the math gets a bit more complicated, the core idea is the same. So let's take a look at a specific example. Remember that figure from the article? About a satellite orbiting at 3 times the Earth's radius. It said it needed to travel at something like 3.9, 4 times 10 to the third meters per second to maintain a stable orbit.
Yeah, I remember that one. It really shows how precise those space missions have to be. That calculation was for a very specific scenario, a perfectly circular orbit at a fixed distance in the real world. Mission planners have to take into account tons of different variables. Things like atmospheric drag, the gravitational pull of the moon and the sun, even the fact that Earth's own gravity isn't perfectly uniform. All those things can affect a satellite's motion.
That was incredibly complicated, like a puzzle with all these forces pushing and pulling on the satellite. How do they ever get it right?
It takes super precise calculations and a deep understanding of orbital mechanics. Even a tiny miscalculation can have huge consequences. Imagine, if a satellite is supposed to observe a specific area of Earth, but its orbit is off by just a little bit, it could completely miss its target.
That's a good point. It's like trying to hit a bullseye on a dartboard that's moving around. So we've talked about getting a satellite into the right orbit, but what about keeping it there?
That's another big challenge. It brings us to something called orbital decay. Even hundreds of kilometers above Earth, there are still traces of Earth's atmosphere. And over time, those tiny atmospheric particles can cause drag on a satellite, slowing it down.
Wait a minute, so there's still air friction way up there? I thought space was a vacuum.
It's not a perfect vacuum, especially not in the region where a lot of satellites orbit. That's called low Earth orbit. It still has enough particles to cause a little bit of drag.
So what happens when a satellite slows down because of that drag? Does it eventually just spiral back down to Earth?
Exactly, if nothing's done to stop it. As a satellite loses speed, its orbit decays, meaning it spirals closer and closer to Earth, eventually. It enters the thicker part of the atmosphere, where friction increases a lot, and it heats up and burns up or breaks apart. That's why a lot of satellites, especially those in low Earth orbit, need little boosts every now and then to stay up there and prevent orbital decay.
It's amazing that something as small as those air particles can have such a big effect on a satellite. It really shows how delicate this whole orbital balance is.
It does, and it shows that even in the vastness of space, there are all these forces constantly acting on objects like satellites.
This has been so eye-opening, but I have to admit, my brain is starting to feel a little full with all this information.
I get it, we've gone through a lot. From the basics of orbital speed, to the complexities of elliptical orbits, and the challenges of orbital decay. It's a lot to process.
I think it's time to move on to that last topic you mentioned, different types of orbits and how they're used for different missions.
Absolutely. Let's dive into that.
Okay, so we've talked about orbital speed and elliptical orbits, and even how those tiny little air particles can drag satellites back down to Earth. Before we started this, I thought satellites just kind of floated up there, but it's way more dynamic than I ever imagined.
It really is. And all those things we talked about are really important when deciding what type of orbit is best for a particular mission, especially for space exploration.
Okay, so we've mostly talked about satellites orbiting at different distances from Earth, but are all the orbits pretty much the same besides that?
Not at all. Orbits can have different shapes, different inclinations, and even different purposes. Some are designed for communication satellites, others for Earth observation, and others for scientific research.
So what are some of the most common types of orbits?
Well, one you've probably heard of is geostationary orbit, or GEO for short. Satellites in GEO orbit at a very specific altitude, about 35,786 kilometers above the Earth's equator, and they orbit at the same rate that the Earth rotates.
So they're basically staying in sync with a certain spot on Earth.
Exactly. From our perspective on the ground, a geostationary satellite appears to stay in the same spot in the sky. That makes them perfect for things like communications and broadcasting, because you can just point a satellite dish at that spot and always receive a signal.
That's pretty cool, like a giant antenna in space.
Mm-hmm.
What about orbits that do move relative to the Earth's surface? What are those used for?
Those are called polar orbits. Satellites in polar orbits travel from pole to pole, passing over different parts of the Earth as the planet rotates underneath them.
So they're constantly scanning different parts of the planet.
Exactly. Which makes them ideal for Earth observation missions, like weather forecasting, environmental monitoring, and mapping. They can provide a really complete view of the Earth.
So different orbits are like different tools for different jobs.
I like that analogy. And there are tons of different orbits in between GEO and polar orbits, each with its own pros and cons. You've got medium Earth orbit, or MEO, which is often used for navigation satellites like GPS, and low Earth orbit, or LEO, which is becoming more and more popular for things like space tourism and those huge networks of internet
Wow,
satellites.
so many possibilities.
Yeah.
Since we're talking about different types of orbits, remember how we discussed that the International Space Station isn't in a perfectly circular orbit?
Right. The ISS is in what we call a slightly elliptical orbit at an altitude of about 400 kilometers. So its distance from Earth changes a little bit throughout its orbit, which also means its speed changes.
So even the ISS, this incredible example of human achievement in space,
Yeah,
has to follow the same laws of physics as every other satellite.
exactly. It shows that even in space, those fundamental forces are still in control. And those little changes in the ISS's orbit actually have some interesting effects. Like the amount of atmospheric drag it experiences changes throughout the orbit, which can affect its altitude, and sometimes it needs a boost to keep it from falling back to Earth.
That's incredible. It makes you appreciate how complex and amazing space exploration really is.
It really does. It shows why understanding orbital mechanics is so important, not just for launching satellites, but also for keeping them running and making sure they can do their jobs.
Well, I think this has been a fantastic deep dive into the world of satellites and orbital mechanics. We've learned about the basic physics behind orbits, the different types of orbits and what they're used for, and the challenges of operating in space. I've learned so much.
Me too. It's been a pleasure exploring all this with you, and I hope it's made you even more curious about space and the way things work up there.
Absolutely. So to everyone listening, keep looking up, keep asking questions,
Yeah.
and never stop exploring. Who knows what else we'll discover out there?